So, second speaker of the afternoon session is Andras Vasy from Stanford University. So, he got his bachelor degree from Stanford University in 1993. His major was physics. And simultaneously, he got a master's degree in the same year from Stanford University. Then, in 1997, he got his PhD from MIT. So when he got some PhD, he got some Jennifer Johnson Prize for best research papers. Okay, his title of talk is some recent advances in microlocal learning.
Thank you very much. So let me start by thanking the organizers of the conference and the program committee for the invitation. And I also would like to thank the audience for staying till the hopefully not too bitter end. So what I'll talk about is some advances in microlocal analysis. So of course there's a sum here because a lot of other things happen. I will concentrate on particular problems, and in fact I will concentrate on a very particular one of these because of time limitations. So I think I'm a bit too ambitious here, and I really do want to get to the microlocal analysis aspect. So the sort of things I want to talk about in terms of applications are what have bullet points here. So one of them is the analysis of the Laplacian and asymptotically hyperbolic or conformally compact spaces. So this is something that I will explain. And this is also related to the asymptotically de Sitter, the Lambertian. Now, something that's somewhat different but related is, in a slightly roundabout way, is wave propagation on Kerr de Sitter space. So you heard a lot about Kerr space-times. So this is the positive cosmological constant version. And so here what I talk about, so I will basically talk about linear analysis because what I really want to get to is microlocal analysis. There are some nonlinear results on this with my student Peter Hintz on this, I mentioned briefly. And the last thing that I really say very little about, but I just do want to say, show the variety of things that can be done, is about the meromorphic continuation of the real zeta function for Anosov flows. And so I'll say more about it in a moment, but the microlocal analysis work here is that of Jatlov and Zworsky, and so Jatlov is here in the audience. And so what I would like to emphasize is that all these work by placing these problems into a non-elliptic Fredholm framework using microlocal analysis. So let's see how this works. All right, so let me just say first what asymptotic hyperbolic spaces are. So it's not necessarily the best way of saying this because I'm not putting just the minimal amount of data and things like that. So the easiest way to think about this is you start with a compact manifold with boundary. So of course, maybe before saying this, let me just say that hyperbolic space or certain portions of it, they're supposed to be good examples. And so you're supposed to think of something like the Poincare-Ball model of it. Or locally, the upper half-plane model is, of course, perfectly fine. So, so think of an n-dimensional compact manifold. And just to get started, it's easier to say that you take a preferred boundary defining function, so something that vanishes at the boundary and does so simply. And then you have a complete Riemannian metric on the interior of this compact manifold with boundary, which behaves in a certain way at the boundary. So namely, if you multiply it by the square of the boundary defining function, you're going to get an honest Riemannian metric on this compact manifold with boundary. So it's smooth now up to, including at the boundary. And it's honestly Riemannian, so honestly non-degenerate. So two statements being made for smoothness and non-degeneracy. And then an actual normalization, which is, in terms of geometry, an asymptotic curvature, sectional curvature statement about the norm of the boundary defined function relative to the actual Riemannian metric, I mean the one that's Riemannian at the boundary. All right, so that's, and again, of course, hyperbolic space or various things like that will be an example, but it's the way you should think about this is that it's an example in the sense that, say, a manifold is Euclidean space is an example of a manifold. So namely, at each point on the boundary, somehow there is a similarity to hyperbolic space, but this particular similarity can vary with where you are. All right, so it's like a variable coefficient version of hyperbolic space in some sense. And so the boundary here is metric infinity, but it's very useful to think of this as really encoding the structure via this compactification. All right, so if you take such a metric, this is a complete Riemannian metric, so the Laplacian functions for now is going to be essentially self-adjoint and complex coordinate smooth functions on the interior, and then you can consider this modified resolvent. So this is modified in two ways. I subtracted this constant from it, and then I replaced the parameter sigma, with lambda, say the usual spectral parameter, by sigma squared. This is just for convenience, it's a re-parameterization of the spectrum. And so what you get, and so let me just say explicitly, so what happens is that the spectrum a priori would be a subset of the non-negative half line of this operator on L2, that is. And then, in fact, the essential spectrum starts at this constant n-1 squared over 4, so it goes on to plus infinity, and then this map, sigma, goes to n-1 squared over 4 plus sigma squared. What it does is an identification of the open upper half plane with the complement of this line n-1 squared over 4 to plus infinity. So just sort of opening up the spectrum is what it does. So this is sort of a convenient way of writing things. And then, so it exists as a bounded operator when on the upper half plane minus this segment, which is just a segment corresponding to 0 to n-1 squared over 4 that possibly has points in the spectrum, but not in the continuous spectrum, which is a convenient parameterization. All right. So, one thing that's useful to say here is that if you take a good product decomposition, which might require changing this boundary defining function x, then such a metric G0 has this form. So it's like dx squared plus h, where h is now a family of metrics on the boundary, or sort of slices that look like a boundary, which depend, on the other hand, on this boundary defining function, this parameter. So you have a family near the back, in a color neighborhood of the boundary, the manifold looks like a family parameterized by x of the boundary, and then for each value of x, you would have a metric, which depends smoothly on x. And so what's useful here is to introduce a notion which is the evenness. So metric is called even if this, so G0 is called even if this h is even in x. Other way to put it is all odd derivatives vanish with respect to x when you put it into this form. All right, so you'll see in a moment why this is useful. So a theorem of Mazzer Narrows from 87 is that, again, on functions, this modified resolvent, which is defined when the imaginary particle sigma is large, in fact has a meromorphic continuation with finite rank pose. So these are called resonances. So what we are doing in terms of the standard spectral picture is that we are analytically continuing across the spectrum. Of course, we cannot continue as bounded operators in L2. We are continuing in a different sense, say as Schwartz kernels. And what we get is, in fact, a meromorphic continuation with finite rank pose, except possibly certain essential singularities on the imaginary axis. And then what's even better than this is that Guillermo in 2003 in his thesis proved that in fact you don't get these essential singularities if the metric is even. So if the metric is not even, you could get some essential singularities. Okay, so now let me just say a word why you care about this analytic communication. Well, there are many reasons, but here's just one example. One example is if you look at the wave equation, so it's Klein-Gordon, as I wrote it just because of the parameters in the spectrum, then if you want to know the asymptotic behavior of solutions of this equation, so what happens as t goes to plus infinity, then in fact this has an expansion in terms of, this is just analogous if you, what would happen if you looked at compact manifolds, Riemannian manifold across time. You want to know what happens to solutions as time goes to infinity, while you get oscillations corresponding to the eigenvalues. So here, what happens is that you get oscillations, these e to the active sigma j's, but of course the sigma j's are now not real. So these are damped oscillation corresponding to these resonances. And so this is sort of an analog of spectral data for in sort of compact manifold without boundary settings. So, so anyway, so this is just one application, and so there are a bunch of reasons why you care about these. Now, what I want to tell you is about, so one issue here to do this is in order to actually get this result from the analytic continuation, meromorphic continuation of the resolvent, you really need to do a contour deformation. In order to do a contour deformation, you have to be able to control the resolvent when this parameter sigma is large, it's close to being real because we integrate essentially along the spectrum, it's close to real. You have to be able to control it in strips. And basically how much decay you want to get determines how wide your strips are. So what's the imaginary part? And so this was actually a difficult problem. So what I would like to tell you about, mostly, is how you can do this, how you can get these high energy estimates for the analytic continuation. This also will give you a new proof, in fact, of the very fact that you have a meromorphic continuation, and also gives an extension to differential forms in a natural way. So here's the result. So on n-dimensional asymptotic hyperbolic spaces, on functions, this modified resolvent continues meromorphically, and if the so in order to get these high energy estimates, you need to assume something about the geodesic flow, namely a non-trapping property. So if it's non-trapping, so all geodesics escape to infinity, so that's the boundary in the compactified perspective, then in fact you get what we call non-trapping estimates. So estimates as good as they possibly could get on suitable Hilbert spaces, which I don't specify, although you will be able to guess once I get a bit farther into the talk. So, so you get sort of as good estimates as you possibly could, and then there are completely analogous estimates on differential forms, K forms, except that when I defined this resolvent, I had this n-1 squared over 4. In fact, what you have to put in is n-2k plus -1 squared over 4, where k is the degree, and then what this corresponds to is closed versus co-closed form. So you can see that something funny is going to happen when you do this. So this is the actual sort of application of the analysis I would like to get to. The basic idea, which also already gives some feeling of what kind of things one has to do, is to connect a differential operator, which I'm calling here P sigma, on a manifolded boundary which extends this compact manifold with boundary at 0, so it's going to go across the boundary, to the spectral family of the Laplacian. So actually P sigma here is the bottom, so there's no suspense. And so what's happening here, as you can see, is that the spectral family of the Laplacian, it's important, this is the whole spectral family we are talking about, is being conjugated by something which I'm calling mu. And as you see somewhere up there, this mu is actually just the square of the boundary defining function. So it's conjugated by a power of the boundary defining function, in other words. And then there's an extra division by a power of mu. So I did it symmetrically so that there's a mu to the 1/2, whatever this is, mu to the -1/2 on both sides. But this is just a conjugation. And so you can just do a calculation. So I try to later on try to tell you a better reason why this works. You can just use computation, and what you get is an operator that looks like this. So again, mu here was x squared, so when you want to think invariant, more invariantly, what you've done is one introduced, so we started with this smooth manifolded boundary, x0, with defining function x, boundary defining function x, and we changed the smooth structure by introducing x squared as a new defining function. So it sounds like a very small thing to do, but it's a very useful thing to do, because once we introduce this, we did this conjugation, so it's not critically important for doing the conjugation, but if you write your operator in terms of this mu rather than x, so that's I mean, one direction it's a smooth change of variables, but in the other direction it's of course singular, or that's homeomorphism. This new operator continues very nicely and smoothly across mu equals 0, so mu can become now negative, and it does so in a non-degenerate way, where non-degenerate, of course, depends on what you can do. So what's degenerate? It's much more non-degenerate than if I was trying to do the same thing with x. All right, so the point of view now is that we extended this manifold a bit across mu equals 0 to mu negative, and then it depends on what you want to do. So maybe you want to glue 2 copies of this together. There are many things you can do to deal with this. There's sort of no extra. I mean, this minus delta 0 is not an issue. All right, so just to see why, I mean, this is of course a computation you can do, but it's much nicer to try to get a slight feeling for this. And so what happens is that just at the level of the principal symbol, so just at the highest order terms in the operator, if I go back, is that this conjugation I'm doing here is completely irrelevant. That's only changing low order terms. So I'm just dividing by mu inverse. I'm multiplying by mu inverse. So what does that do? Well, the principal symbol of a Laplacian is just the geometric function. So if I write it out in this way, this is what it is. And all I'm doing really, so I'm changing from x to mu. So x dx is the same as 2 mu d mu. My original dual metric was something like x dx squared plus x squared times a metric in the y variables, dual metric in the y variables. Well, the x dx squared became the mu d mu squared. Again, this is just a dual metric, so I'm just writing it like this with a factor of 4, but that's harmless. And then my x squared became a mu in front of the h. And so I just factor out the mu. Again, this is just a tensor, so it's not an actual differential operator we are talking about. Factored out the mu, and so that the division by mu just leaves what's here. And that's exactly the principal symbol, if I copied things correctly, of what I had before if I managed to go back. So that's exactly the principal symbol, it's P sigma. Okay, so this was the this is what happened at least at the leading level, and what you can see here is an operator that's what's left here is the principal symbol itself is something that's elliptic when mu is positive, is hyperbolic when mu is negative, and then there's a transition at mu equals 0 that involves what's called radial points. So in fact, you could think about it in a different way, mu negative. You could start instead, so I talked about essentially hyperbolic spaces, or Lorentzian Riemannian conformally compact spaces. So instead you could start in the Lorentzian category and do similar things. So the analog of hyperbolic space, there are two reasonable analogs depending on what signature you'd like to have boundary to have. So the relevant analog is de Sitter space, which, so one way to think about what it is, maybe later on I will have a slide, is that hyperbolic space is 1/2 of the two-sheeted hyperboloid in Minkowski space of one higher dimension, while the Sitter space is the one-sheeted hyperboloid. So anyway, and there's a sort of natural generalization of this, the Riemannian structure introduced in the, or rather Mazzian-Marrow introduced in the Lorentzian world. This would be essentially the Sitter version, which again is somewhat at each point on the boundary of the compactification is de Sitter asymptotically, but sort of different de Sitter space in some sense. So if you did the same sort of thing there, then you would get a very similar result, but there would be one difference, which is that, so I'm calling x tilde the boundary defining function, and what I would do is I'm going to link the two problems, I will have this mu to be equal to minus x tilde squared. So now it's negative, and then it's the same mu as above. So what happens here at the formal level is that this function is x squared in the Riemannian setting, so x is positive, and minus x tilde squared in the Lorentzian world, so again x tilde is positive, so this is positive, this is negative, are somewhat exactly the same. So what this continuation across the boundary, this funny continuation across the boundary is doing is really linking a Riemannian and the Lorentzian problem, an elliptic and the hyperbolic problem in the PDE level. Okay, and so what this is in some sense is mathematically a mathematically precise way of doing a Wick rotation, right? So I mean I'm going from mu positive to mu negative, and because of the square in the definition of x and x tilde, this amounts to putting an I into x. That's what the Wick rotation would be what physicists do. All right, so so this is going to be the part that I'm going to start skipping, but at least I want to say a few words about this. So this is to relate to the curved de Sitter picture. So I told you that the Sitter space is the one-sheeted hyperboloid. The Sitter space itself is the one-sheeted hyperboloid in one higher dimensional Minkowski space. Now, one thing that's relevant when you're doing conformal geometry is that while geodesics, of course, change drastically when you have a conformal factor, now geodesics just get reparametrized. So the non-geodesics on the Sitter space would be the same as on a finite cylinder, so sort of 45-degree angle lines. And then the other nice thing is when you talk about wave equations that you can do something that's sort of just too good from an elliptic perspective. Namely, you have this finite speed of propagation. You can solve equations just in certain subdomains. So an elliptic equation you'd never expect, right, that you could do that. sort of unjust that you can do that. Okay, so so the upshot is that when you are in the Sitter space, you can just decide that maybe I'm just going to solve. This is sort of, I picked a point on top of this compactification. I took a backward light cone, and then one thing you can do is just solve a problem in this backward light cone. So say the Cauchy problem with data here, just solve it in omega plus. So you can do that. That's sort of course, a much weaker thing than solving the problem in the whole the Sitter space. But but you know, sometimes that's a good thing to think about. Now, the other picture I drew is what real algebraic geometry would be a blow up. I mean, a sort of spherical rather than a real projected blow up of this point Q plus. So I'm distinguishing directions of approaching this Q plus. And the reason why I did this, because if I now think of this as a smooth manifold, then there's and so again, of course, nothing changed. I just changed this compactification. I'm still trying to solve problem only omega plus. Then this, in fact, is very close to, and so in fact has almost all features of a curvy Sitter space that I mentioned earlier. So, okay, so I'm not, as I said, I'm not going to talk about curvy Sitter space because otherwise I'm not going to get to my main point. But let me just say that there's only one sort of novel extra feature that you have to deal with, which is, well, okay, there are two things I should say. So one of them is trapping, and the other thing is, what's even more interesting, is that the behavior of waves as you approach what would be this, I'm trying to go backwards too much. What happens when you approach this, what I would call here front face, that's FF. So that depends on so here it's all very easy. It's given by some power of the defining function. So of course here it's the same picture, so the same thing is true. But if you generalize this, then it's given by sort of quantum data, and these quote quantum encode data are resonances. So they're poles of a family of operators, which is very similar to this extended operator we had in the continuation of asymptotic hyperbolic Laplacian, so conjugated family. All right, so as I said, the main extra ingredient is apart from this is trapping, and just so that I do justice to him, so this is in this work I did on this, the main external ingredients of the work of Wunsch and Zworsky. Since then, this has been extended and improved by Nonema, Zworsky, and Yaklov. So I'm not going to talk about this, and I'm not really going to say the theorem. So this is just the asymptotic expansion. And of course, we already heard, for example, Mihalis the friend was talking about curved space-time. So there has been a lot of work, especially in curved space-time, where of course you can expect less. You can only expect polynomial decay, but these sort of expansions give you an exponential decay in this case. And maybe just mention one more thing, which is that you can also solve nonlinear equations with this sort of approach. So let me skip that. Oh yeah, so one thing I should say that in case you're desperately trying to take notes, which is probably not the case, but in case you are, in fact these slides are on my webpage. So I didn't put my webpage on the first slide like Robert McCann, but you can just Google my webpage and you'll find it. All right, so anyway, so the third setting, which again I'm not going to say much about, except that it exists, is this dynamical zeta function for Anosov flows. And so what is an example of this is supposed to be surfaces of negative curvature. So that is to say, you look at the cosphere bundle on surfaces of negative curvature. And what happens is that you have and so of course we're having a lot of talks here at the ICM on dynamical systems. So it happens that you have a stable and an unstable distribution. So in stable direction, if you perturb, you get exponential convergence. In the unstable, you get exponential divergence in future times. Of course, in backward times, everything goes backwards. So reversed. So a conjecture of Smales from a long time ago, the 60s, which was proved recently by Giulietta, Liverani, and Polycott, is that the zeta function you can define by this has a meromorphic continuation. And then what I would like to say is that, so this is a relatively complicated paper. Of course, complicated depends on where you come from, so what your background is. But what I would say is that Jan and Swirsky gave a pretty short proof, which is essentially self-contained, meaning that they actually have an appendix writing up the microanalysis results they use shortly afterwards. Sort of independent. I mean, it was an independent proof, except that, of course, by that time this had been done. So I should say that their proof uses microanalysis, which is inspired by these ideas of Four and Scherstrom. And so it's similar to what the sort of tools that go into the theorems I mentioned, as well as Guillemin's trace formula approach. So again, maybe I'm not really going to say what it is, this theorem. So it's again a meromorphic continuation of a zeta function. Again, there has been much work. I mean, this is all very recent. So there's been work of Jakob for Guillermo for G on sort of related things. Okay, so I think that's the general stuff I want to say. Let me see how I'm doing time-wise. Okay, not too bad. Okay, so what's the setup? So the way I think about this problem is sort of a Fredholm setup. So what you want to work on some operator, I mean some manifold with a boundary or corners or whatever, and you're going to have some Hilbert spaces of functions, or maybe Banach spaces, but Hilbert spaces are fine for what I want to do. You want an operator that maps between them continuously, has closed range, fine-dimensional kernel and co-kernel. And so this is guaranteed, so it's a Fredholm operator. So this is guaranteed by these Fredholm estimates. So it's an estimate for the operator and an estimate for the L2 adjoint of the operator. So the adjoints are taken relative to, I mean, I'm really going to think about function business manifold, so adjoints are relative to L2. So this is a formal adjoint here. And so there are these error terms, and the inclusion into the error terms of the left-hand side are supposed to be compact. So I'm going to give you examples in a moment. Right? And this is sort of the standard setup. And so, of course, as I said, this is a Fredholm estimate, so almost invertibility of the fine-dimensional obstacle. Sometimes you want actual invertibility, of course. Another interesting question you might want to ask is the index of these operators. All right. So, as I said, typically this is considered elliptic or Riemannian settings. But I mean, you can of course solve wave equations. So, if you set up your function spaces correctly, then you should also get a Fredholm statement. I mean, you can solve them uniquely, right, with the correct data formulation. So I want to discuss exactly such non-elliptic problems and so more generally. And in fact, I mean, I should also ideally talk about a boundary setting, which I'm going to completely ignore just because there's no time. So in fact, there are different things. So the most directly relevant one would be what Melrose would call B analysis, but there's also like scattering analysis and various other things. In this B analysis, that's most relevant to the result, second result I stated. So then one would work with weighted Sobolev spaces, and the extra bit of thing that you would need to get Fredholm properties is that you have to choose the weight correctly, so it's not the imaginary part of any of the any resonance. So the resonance is sort of posed in this meromorphic continuation. All right, but I'm going to ignore this completely. So all right, here it is. So we're going to do microlocal analysis now. And so at least I should say a few words about this. So this is analysis, local analysis on phase space. So I mean, for physicists, phase space is or mathematicians, phase space is the cotangent bundle of a manifold. And in fact, these sort of structures we want to do, because we're not doing semi-classical analysis right now anyway, really are sort of homogeneous. So we're thinking about dilations in the fibers of the cotangent bundle minus the zero section. So in other words, we're really working with the cosphere bundle. So the cosphere bundle is really a quotient by the dilations in the fibers of the cotangent bundle. And so this analysis is done by two differential operators, which in local coordinates are just given by oscillatory integrals, and sort of an obvious generalization of this. And of course here the question is, so this is P is acting on a function U, and the question is what is this amplitude little p that you put in? And so typical example, I mean this should be simple, but I'm going to say what the symbol is. So typical example is that asymptotically, so asymptotically means that the relevant regime here is what happens is psi. That's sort of the dual variable, the momentum variable, fiber variable, cotangent bundle. What happens is that goes to infinity. That's a merit. And so the two basic structures, most basic structures that you want to talk about are the principal symbol of the differential operator, which is a function essentially on the cotangent bundle, and captures two differential operators modulo lower the two differential operators. So these get bigger, these classes get bigger as m increases. So the rough guide is differential operators of order m. That would be sitting in here. So it captures the operators modulo lower order operators. So there's a short exact sequence, for example, if you're so inclined. And the other notion is the wavefront set of an operator. So this tells you what the operator is to leading level. And the other object is this wavefront set, which is a subset of this cosphere bundle. So again, here it was a function of the cotangent bundle, but it's really a homogeneous object, at least essentially. So it's really a function of the cosphere bundle, in some sense, or a line bundle over it. Anyway, the wavefront set, which tells you where in the cosphere bundle the operator is not trivial. So what's trivial? Trivial means that it's an operator of arbitrary low order. It's completely trivial. It's Schwartz as psi goes to infinity. Okay, and so as in fact was even mentioned in the Chern notation for differential operators, the principal symbol just captures the leading part. So the simplest example is elliptic two differential operators on manifold without boundary, which is actually the setting which was mentioned in the Chern lecture. So you add between sections of vector bundles, the most basic examples being like the Laplacian differential forms or Dirac operators. And so ellipticity is an invertibility condition on the principal symbol, which is a function on the cotangent bundle, or the cosphere bundle essentially. And in this case, as your function spaces, you would typically take Sobolev spaces, and they're just corresponding to the order of the operators is a shift by m in the spaces. And then these are the IL10.12 spaces, and then you can take as your error spaces horribly negatively ordered. Very weak norms is what it corresponds to, very weak norms on the right-hand side. And so the Fredholm property is just the elliptic estimate in this case. And again, you really need it for both the operator and for its adjoint. For an elliptic operator, the adjoint is automatically also elliptic, and you need it for the dual function spaces. So, so here the choice of S is irrelevant. That's elliptic regularity. All right. So. See if this works. Okay, so in non-elliptic problems that we want to think about, the estimates we will have are sort of this kind. So this is the loss of one derivative. This is exactly the same loss of one derivative as in the wave equation that we heard in the previous talk, Jeremy's talk. And then, of course, you want a similar estimate for the adjoint, the L2 adjoint. And here, the numerology, again, you want sort of dual spaces, and so this is the actual numerology you want. Now, here, to get the Fredholm property, what sort of spaces you would take. So, say you want the target space to be actually a Sobolev space. So it would be the space corresponding to here. Then your domain should be, well, HS, but it's not quite the right space because after all the operator is losing m derivatives, so you put on this extra condition. So it looks maybe a bit funny, but I mean, invariantly, this is just what would we call the first order quasi-symmetric space. So it's actually invariant motion, and C infinity is dense in it and all that. So it's a nice space. All right. I'm not going to read this slide, but I'm just going to say that in many examples, you want to go, in fact, to non-constant order spaces. So you want to allow the Sobolev regularity to vary based on where you are in the cosphere bundle. So the variable order spaces. And so once you know what type U is, there's an obvious way of doing this. All right. So what's the most basic phenomenon in non-elliptic phenomenon in microlocal analysis? Well, it's the propagation of singularity. So this is Riemann-Dash theorem in 71. So sort of same time, this term of Riemann, the F5 construction. That sort of a part of it was mentioned essentially in Jeremy's talk, so the last version, earlier last version. So what we have here is that first of all we have the wavefront set of the notion of a wavefront set of a distribution. We just measure, so the way you think about this, two differential operators, right, is that you could talk about, what you use them for, is you can talk about what happens in phase space. So on the cotangent, the more precise in the cosphere bundle. So what the wavefront set of a distribution is describing is where on the cosphere bundle a distribution is nice or not nice. And nice here is HS, where you get to decide an S. And so the basic things are that in the characteristic set, one has elliptic regularity, so microlocal elliptic regularity. So this says basically, as long as you're away from the characteristic set of the operator, so where the principal symbol vanishes, if PU is nice, U is nice, right? That's elliptic regularity. And then outside the characteristic set, you have propagation singularities, which is to say that the wavefront set, in this case, again, the HS wavefront set is a union of bicharacteristics. So singularities propagate on bicharacteristics. So here's a picture, and so I mean I stated here as a singularity statement, but of course that's equivalent by the closed graph theorem. It's equivalent to an estimate, and of course you really prove an estimate when you prove this theorem. And the estimate is like this: that you can estimate U somewhere. So psi 0 again. These are like homogeneous degree 0 symbols, so they're honest functions of the co-square bundle, and you think of these as localizing in parts of the co-square bundle. So this says that you can localize U somewhere in the, so if you localize U somewhere in the co-square bundle, so this is where B1 is non-trivial, you get an estimate like this. So you can estimate U here, so this picture is supposed to be that of the co-square bundle. You can estimate U here by estimating U here in the red region, plus estimating, of course, PU. I mean, if you don't know PU, you don't have an equation, so you can't estimate. Estimating PU and sort of the union of the bit bigger region, the union of the two. Okay, and so that's the propagation of singularity. It's such an estimate. And this is only even valid if you have variable orders here. Provided that you, of course, not trying to do something that you are not allowed to do, trying to conclude that you have H trillion regularity here just from having L2 regularity there. All right, so the problem with this is this B2 term, so if we go back, is this B2 term on the right-hand side. I mean, this says that if something is nice somewhere, then it's nice somewhere else. But how do you know that it's nice anywhere? So, okay, let's see if this goes. Okay, so one way of doing this is complex absorption. So this is technically extremely useful, and so it's been used in a lot of results, especially on resonance theory. And so what you would do there, which I'm not going to really talk about, is to add an operator Q. So P has real principal symbol here. You add an operator Q, which again has real principal symbol, but there's an I in front of it. This is what's going to be this absorption, and you want this principal symbol to have the correct sign. And so again, you will want that you will have to have estimates always for both the operator and its adjoint. When you take adjoint, this I will switch sign, so everything is going to go exactly the right way. All right. So a more natural option is to have some structure for the bicharacteristic flow. And so the most natural version is called radial set. So when you have sources or sinks, or a bundle of sources or sinks, this is supposed to be this L, is supposed to be, so this is the quotient by dilations of lambda, which is the actual set, which is sort of the actual source slash sink. So this is supposed to be, again, the co-square bundle. What you have is you have these bicharacteristics that are, so integral curves the Hamilton flow, they're happily converging towards this sink in this picture. And so Hermander's theorem on propagation of singularity says nothing. It says basically that you can propagate estimates along the flow, but so this is, here the flow vanishes, it's constant, so these bicharacteristics never get there, so you don't get any estimates. So just as a remark, in non-degenerate setting, the biggest this thing can get is a Lagrangian manifold, and then this also arises in scattering theory. In fact, the first place where some of this is generally written down is in scattering theory, where it's studied by narrows. Alrighty, so what do you have? Okay, so it's not really important exactly what it says here, but there's some quantity associated to the sub-principal part of the operator P. So P was an order M operator, and it's supposed to have real principal symbols. It's self-adjoint to leading order, but one order below it doesn't have to be self-adjoint. In fact, in interesting examples, it's not, like in the one I had at the beginning of the talk. But you look at P minus P star over 2I, it's going to be one order lower, and you basically want to know about its principal symbol. So it doesn't really matter what it is. Anyway, the upshot is that the theorem you get at radial points is something that depends on this number, on the sub-principal symbol, just at this radial set. And the theorem you get depends on whether you're trying to propagate estimates from or to the radial set, or to put it in a different way, depends on the Sobolev order, whether it's higher or lower than a certain threshold regularity. And so the Sobolev order is higher than this regularity, then you can actually propagate estimates from L. So this was, oops. Well, anyway, so if you're higher than this threshold, then you can propagate estimates from this radial set without this a priori term. While if it's Sobolev order is below this, you're in a rough space, then you can propagate estimates to L if you just have control of, so up to including L, if you have control and puncture neighborhood. So this is the sort of thing that happens in scattering theory. Like this is the sort of thing that in a not fully microlocal way went into, for example, the analysis of the n-body problem, quantum n-body problem. So anyway, here's the estimate version. So as I said, if the Sobolev order is high enough, bigger than this threshold, you get an estimate like this without that annoying B2 term, while if this regulator is low enough, you get the B2 term. And then another remark here is we change P to P star, that sort of changes the sign of this constant here, and so that naturally gives rise to the dual space. It's just what you need for Fredholm estimates. So the upshot overall is that if you have a problem, so you work in a compact manifold, say, for start, because this was the easiest thing, and then our phase space naturally is the co-sphere bundle of this. And suppose you have a non-elliptic operator. So of course everything is elliptic and everything is great, you have to work. Suppose it's non-elliptic. So, and let's suppose it has real principal symbol, which is sort of the most natural thing. And so then what you will have is this bicharacteristic flow. So the Hamilton flow inside this characteristic set. And in general, you expect that maybe this is a completely chaotic flow, and you can't really say anything. And then you have a problem because where do you start? But if you have a nice flow that starts from somewhere and ends somewhere else, so you have sources or sinks, or bundles of sources and sinks, that start at one of them, ends at the other one of them, and you can cook up your Sobolev orders, so this might be variable, such that they go sort of the appropriate way, then the estimates I told you just piece together to give you the Fredholm estimates you really want. And so here's a picture. So this is in fact would be the picture if you identify these two sides and these two sides. This is the picture if you Fourier transform the flat Laplacian minus a constant in Euclidean space. That would be the characteristics, the bicharacteristic flow picture on it. So again, here this is the source. This is the sink. And so the flow just goes from the source to the sink, and so you want to have a Sobolev space which has either a bit bigger or a bit lower regularity than the threshold here, and the opposite regularity here. For the adjoints, of course, all these would reverse, so they would go exactly the right way. So the upshot is that, okay, here's the honest example I started with, the asymptotic hyperbolic space. So mu positive was my space, original space, so x positive, that corresponds to mu positive. Once I extend it, what will happen is that my s, so that's mu equals 0, over its cotangent to co-sphere bundle, in its cotangent to co-sphere bundle, I will have radial sets. This is plus and minus. My character, remember the operator is actually like a wave operator, it's hyperbolic. In mu negative, so the flow will look like this. It's to and from these radial sets. And and so here I did not. So I could, so in fact, if you try to do this in some other way, you sort of naturally would get another source and sink here. We have exactly the geometry I described before. An alternative would be to add complex absorption here, which I skipped, or instead a bounder. In this case, you can really just think of this as like a Cauchy problem in this extra place. Just one word. Yes, just say a word about this. So what's a different way of getting the same picture? A much more natural way. I mean, it's wrote down a crazy conjugation. So a more natural picture would correspond to the following. Here's the Minkowski space at one higher dimension. And I think of it as compactified radially, so I just add the ball to infinity. So the way you should really think about this is you start with Rn plus 1, and then you have, well, to separate the origin, you have an R plus action on it, dilations. So maybe at the beginning you would think that the natural analysis for the wave operator is using the Fourier analysis. So here, what you would think is that the natural analysis maybe is using the Malin transform, using the dilation invariant, the homogeneity. I might have to re-homogenize it just to make it nice. So if you Malin transform the Minkowski wave operator, so what's shown in red is the is the two-sheet hyperboloid, and blue is the one-sheet hyperboloid by higher dimensions. So that's the Stichter space, is hyperbolic space. Your Fourier transform, a Manin transform, sorry, and you do the thing that corresponds to a smooth structure. So what's a smooth transversal to the R plus orbits? Well, a smooth transversal would be a sphere. So if you Manin transform, you get a family of operators depending on this Manin dual parameter on the sphere. So that's exactly, in fact, the operator family I wrote down before, and this extended version of hyperbolic space. So extended hyperbolic space is really going from here to beyond. And so this is what, in what sense, it's a projective geometry, or a conformal geometry, what one is doing. On the other hand, if you use a different scale for the Manin transform, a scale that blows up at the light cone, that's sort of the geometric natural scale corresponding to the Minkowski metric. Then when you Manin transform, you get the stacked family of the hyperbolic Laplacian, but then you get something singular at the light cone. So just relating the two Manin transforms, the one that's geometrically natural but singular, and the one that's geometrically not natural but smooth, is really the relation I described at the beginning of the talk. So thank you very much.
Only one question. Okay.
So you have an equation which changes signature.
Yes.
And is it the same change which happens in transonic floors, where you have subsonic floor on one side and supersonic floor on the other?
So I don't know exactly what change happens, but what I know that it's not the same as is another standard change, the Tricomi equation. So that's a different change. So in Tricomi equations, you would not have radial points. The flow would still continue perfectly nicely. I mean, you would not have critical points for the flow. And so what that corresponds to is just switching this mu, whether it's in front of the d mu squared or the degenerate, so it's in front of d mu squared or the Laplacian. So where you put it changes the type.
Okay, thanks again.